What I want to talk about today is a conjecture of Gordon, the cosmetic surgery conjecture. We start with a knot in some three manifolds. We perform Dane surgery, delete the knot. You have some specified framing, which you fill in with a disk, and fill in the remaining boundary component with a sphere. And in practice, the surgery seems to remember the framing in some precise sense. So Gordon's conjecture, here's the version, the phrasing in the Kirby problem list, is that if I take a knot complement, other than the most boring one, other than the complement of the unknot, it's irreducible. If two different surgeries on that same knot, if two different ways of filling in that three-manifold with boundary get me the same result, then there's a good reason for it. There's a homeomorphism from one to the other, taking one framing to the second. Equivalently, if I have the same three-manifold and two different knots in it with homeomorphic complements, you can extend that homeomorphism over the knot. Or better, there's a homeomorphism taking one knot to the other. If you focus on the three-sphere specifically, then framings are parametrized by rational numbers, how many times you wind around the longitude and meridian, respectively. And here, that second statement, there's an oriented homeomorphism taking one framing to the other. If you have a non-trivial knot, that doesn't happen. The statement just says, if I have a knot with two different surgeries, which are the same as oriented manifolds, then the number was the same. Gordon conjectures this partly because he proved part of it the year before. Gordon-Lukey proved that if any surgery on a knot in the three-sphere returns the three-sphere, it's the trivial surgery. You didn't do anything. They use geometric topology techniques like really honest topology, thin presentations for knots, sutured hierarchies. Boyer lines the next year proved that, and here I should say I'm focusing entirely on the case of knots in the three-sphere, just to simplify the story. Boyer and lines proved this for a larger class of knots, knots where the Alexander polynomial has non-trivial second derivative at 0. There's a surgery formula relating Casson invariance on these different surgeries, and by looking at that formula for the two supposedly different surgeries, you get a contradiction if this number is non-zero. After that, there's a long break in progress, and maybe interest, until there's a big result in Heegaard Floer homology, which gives a huge constraint on these numbers. If I pick R, there's only one possible non-trivial choice for T. It's either the conjecture is true, or it's R surgery and minus R surgery. And Jonathan Hanselman, who I think is here today, pushes, oh, I missed one. Sorry. Ravelo-Manana, using the JSJ decomposition and Heegaard Floer yet more, gets rid of some hyperbolic possibilities. Jonathan, who I think is here today, reduces us to the case of just a much smaller list of possible surgery slopes than all rationals, just to the case of 2, 1, 1/2, 1/3, and their negatives. And in all of these cases, 1 over n, he can give some formula for what the genus of such a knot would be in terms of Heegaard Floer invariance or some description. In the case that R is 2, it's very constrained. You have some knot of genus 2. What I want to talk about today is a recent result of myself, Ali Daimi, and Ty Lidman, which reduces this yet further. And I apologize in advance if you haven't seen this before, that my initials are egotistical. What we were able to prove is we were able to rule out all of these 1 over n cases. You can't have one surgery be equal to minus one surgery, or 1/2 surgery be equal to minus 1/2 surgery, or et cetera. The last claim there is just a little bit of nothing really particularly novel. You can just push some known facts about the Alexander polynomial a little farther in this case. We show that the surgery slope must be 2 if we have a counterexample, and it must have trivial Alexander polynomial. And since then, UC Berkeley grad student Cho Yu Ren has shown that if you find a counterexample to the cosmetic surgery conjecture, you can find a hyperbolic one. So at this point, we're reduced to a very specific list of knots. If there's a counterexample to the cosmetic surgery conjecture, you can find one that's a genus 2 knot with trivial Alexander polynomial, which is hyperbolic and has hyperbolic 2 surgery. Probably not, right? But who's to say? I know we're supposed to talk about new structures in low-dimensional topology, but I'll get there in a bit. Let me start talking about some history here. The tool that we're going to use, so I mentioned these older results use Heegaard Floer homology in an essential way, or really geometric techniques special to 3 dimensions. We try instanton Floer homology instead. In some sense, that's in the same spirit as the Casson invariant, since instanton Floer homology it categorifies the Casson invariant. But we look at the instanton Floer homology with a bit of extra data, the Chern-Simons functional. The Chern-Simons functional has been used for a long time in topology. Someone correct me if I'm wrong, but I think the first major application of this idea is Furuda's result that this group, the integer homology cobordism group, which was once thought to be maybe Z mod 2, is actually gigantic. It has a Z infinity subgroup. Since then, and especially in the last decade, I want to say, there have been a lot of advances to this study of homology cobordism using this Chern-Simons filtered instanton homology. There's work of Daimi that gives an invariant, which is related to some of the ideas I'll talk about today. And one application I like quite a lot of Daimi's invariant is Clayton McDonald proved that there is a homology 3-sphere which bounds a homology 4 ball but fails to embed in the 4-sphere. Something that I would have had no idea how to prove if it weren't for instanton Floer theory's special relationship with the fundamental group, which I'll talk about a little bit later. This question, this cosmetic surgery conjecture is not about homology cobordism. Instead, I'm going to be using the Chern-Simons filtration to extract diffeomorphism invariants, or more precisely, oriented diffeomorphism invariants. The orientation is very important here. Okay, so the basic idea here comes from Morse homology. If I take some manifold, a Morse function, or rather a Morse-Smale function on that, I can take the Morse homology with respect to that, set up a complex of critical points, count flow lines between these to define your differential. D squares to 0, and this computes singular homology. The result's independent of that Morse function. But what we'll see later is special to us is we have a space equipped with a special function, a function that I want to keep around as part of my data. If I don't want to find something independent of f, if I just want an invariant of the space with this function, I can do something kind of silly. I can say, OK, let's use this function to cut off the space at specific levels. Let's look at the homology of these sublevel sets. Just as an example, I can take the 2-sphere embedded in 3-space in this way with its height function as Morse function. If I look at this sequence of spaces, pardon me while I try and draw a handle for a second here. Sure. Yeah. We're just keeping track of how this sphere is being formed as a function of time. I get some homology groups as I look at each of these. There's no homology until time 1. When I pick some 0th homology up, at time 0, I pick up some first homology. But at time 1, that first homology goes away again. Until at time 2, I pick up some second homology. This data, how this homology group evolves over time, and in particular, the connecting maps between these, the induced map as I include this into that, form what the topological data analysis people call a persistence module. And I'm going to be studying this persistence module. More precisely, I want to look at a very specific space. If I have an integer homology sphere, Floer's invariant comes from looking at the space of all irreducible SU2 connections over Y. I didn't write modulo gauge there. This is a talk on gauge theory, so this is modulo gauge. This has a function which it lands in R mod Z, which is a little awkward from the perspective of cutting off at 0 in R from the last slide. And it is sensitive to orientation, like it should be if this is going to tell me something about cosmetic surgery. I don't really like that it lands in R mod Z. I don't know what it means to take the preimage of -infinity to 0. So I can do something silly. I can just pull this up to the universal cover, where I now have an R-valued function, and this story goes through without really any change. I can take the Morse homology of the preimage of the Chern-Simons function up to level R, and call this the filtered instanton homology. To go through some properties here, I think the first thing I want to mention about this, because I lifted that upstairs, it has a periodicity. The function upstairs is Z-periodic, and these groups are also correspondingly Z-periodic. I don't want to explain the shift in degree, but the function shifts up by 1. The degree also shifts up by 8. And you get this isomorphism. Shift the degree up by 8, you get a slightly shifted filtration. You start sufficiently high up. You just have Floer's original irreducible homology. You start sufficiently low down in the filtration, you have nothing. This is some sort of compactness statement that there's only finitely many critical orbits with that number in a given bounded range. And I want to use this to extract some numbers that I can use to compare things. Here, I start by defining a function. I say, let's look at the smallest R that survives into the final homology group. So just to give a sense of what that means in terms of the blackboard here, and sorry if you're watching on Zoom and can't see the blackboard, but it'll be in the recording later. Here, there is some 0th homology at R equals infinity, and the first time that appears and survives forever is at time 0. Time -1. There is some first homology, but it does not survive. It appears and then goes back away. So there is no real number for which that map is non-zero. We're generally telling me that the kappa invariant is infinity for any integer other than 0 or 2, whereas No, the infimum of the empty set is plus infinity. The last thing is we get some degree 2 homology that finally pops up starting at filtration level 2. So I get this function. And functions are all well and good, but both because I want to think less hard, and for a technical reason later, I'd rather turn this into a single number. I want to keep giving. I guess we just had to talk about adding more information, about categorification. And I'm removing as much information as I can to get something I can work with. This function is periodic in a sense. It has a shift as I go up degree by 8. So getting rid of that periodicity, it can just kind of minimize the values of the function. That minus d over 8 factor is to guarantee that there's only finitely many values here. So minimum makes sense. In this example, let's see. I'm taking the minimum of, I think I can do this, minus 1, 2 minus 2/8, which I think is minus 1. Nope. Is there anything I can talk about so far before moving on to how we're going to use these things? So I have these numbers. Oops. I have these numbers. They satisfy some properties. You know, you get some non-zero value when your homology groups are non-zero. You get some finite value when the homology groups are non-zero. The reason this is helpful to me, the reason I like to reduce as much as possible just to these numbers, is that not only is instanton Floer homology a TQFT, when I have a cobordism, I get an induced map, so are these filtered versions. More precisely, the way you define this cobordism map is you write down some cobordism, you look at solutions to the ASD equation on the cobordism, and you count solutions to that with prescribed limits. And if you look at if you compare the limits of such an ASD connection, you find that their Chern-Simons functional drops by the energy of that connection. Energy is non-negative, so I get an inequality here. What's more, the energy of an ASD connection is 0 only if it's a flat connection, only if it is coming from a representation of the fundamental group. So this inequality is strict whenever the fundamental group is 0. I mentioned earlier this stuff connects back to the fundamental group. As Peter mentioned, you can kind of see this in that instanton Floer homology wants to be something like the homology of the representation variety with some correction terms. And here you see applications to the fundamental group corresponding to that. Yeah.
Kind of like discrete poset type of this filtration because of the fact that you have to perturb?
I mean, so there's only an issue at finitely, well, a compact set of points.
Yeah, that's what I mean. Like, so,
Okay,
so
it
you're
doesn't
not really,
matter.
like, you're not, I mean, but you're using the perturbed Chern-Simons values?
Yeah. To make sense of any one of these values, you perturb, but you get something well-defined. And you can complete it to all values in more or less any way, and it's not going to affect the results here. Yeah, there's secretly perturbations everywhere here, but correspondingly, if you start with a Chern-Simons function, a flat connection with Chern-Simons R, you plug it into your induced map, you're sent to some flat connection with Chern-Simons at most R, and in fact, it has to drop if the fundamental group is trivial. You get some induced map, which takes you downwards in size. And what we get is the following lemma. The following lemma is where all of our results are going to come from. If I start with a cobordism, which is simply connected to get this positivity, has b plus equals 0, because I don't like that term I haven't really discussed here. I don't like that minus 3b plus, has injective induced map on instanton homology. This TQFT induced map is well, injective. And lastly, Y doesn't have trivial instanton homology, so that the invariant will end up being non-zero. Then I can distinguish them using these invariants. We'll be able to distinguish a whole family of manifolds by saying the numbers associated to them are different without having to compute a single one of these numbers. I can tell you the computation of a single one of these numbers if you want, but we don't need to. The proof is fairly straightforward. You start with non-zero. If the instanton homology is non-zero, then there's some non-zero filtration level. Like there's some in degree D for which the filtration is non-zero and some high filtration level R. So I look at this diagram. I start with some element X up here, which survives under this left map. We know that exists by hypothesis. The bottom map is injective. So if I start with X up here, go down and then right, I end up with something non-zero over here. So it was mapped to by something up here. And the map from Y prime at this energy level is non-zero. So Y prime has smaller invariant, and we're finished. The hard part is finding a cobordism that satisfies this list of properties. And to be clear, the third one is the really messy one here. Instanton homology tends to want to be non-zero. So the fourth one, you have to check something, but it's true in most cases in practice. Pi1, B+, these are algebraic topology conditions. They're something that we're very familiar with working out. But seeing if an induced map in instanton homology is injective, that requires a lot of control. So whoops, you didn't see that. So I'm looking for some place to find some control over induced maps in Floer theory. And really, one of the only places I know how to do that is coming from surgery triangles. If I look at Floer's original surgery triangle, this relates the instanton homology of zero surgery on a knot in an integer homology sphere to, here I wrote one surgery on that same knot, and to the instanton homology of the manifold we started in. Here I'm starting in the 3-sphere, which has trivial instanton homology. So I know that top cobordism map is an isomorphism. I can do it again. I know that the instanton homology of -1 surgery agrees with the instanton homology of 1 surgery. I have cobordism maps inducing these. So why am I not happy? B+ is 1. I just lose. I get some control over this hard condition at the cost of one of the easier conditions. We get nothing. We're on to new structures now. Just to give some context for where the result comes from, because at this point we were just stuck for a while and we just moved on. A lot of my work focuses on an equivariant version of this. Here I'm talking about Floer's irreducible instanton homology, which is designed to not pay attention to the trivial representation of the fundamental group, or abelian representations more generally. And a lot of my work since I got my thesis has been saying, no, you really should pay attention to those. There's a lot of good stuff in there, even if it's hard work. On the other hand, today I'm talking about the group you get by ignoring those. So I want to try and say why one should tell me something about the other. If I look at this C tilde, well, in a moment you'll see that it's relevant, that it's defined for rational homology spheres, and not just integer homology spheres. But also, Floer's group is part of the data somehow. It's the irreducible only part of the data in this group. So maybe some insights I have about the big thing gives me some insights about the small thing. This is kind of directly related to the collaboration. I was thinking about these groups C tilde, and I was trying to study surgery triangles in instanton Floer theory, and it gets to be a mess when you leave the classical setting. And I was just playing around with knots in RP3 as a test case to start somewhere, one of the simplest non-integer homologies 3 spheres I can think of. I prepared some talk about this, and what it what I realized along the way is that this has something to say about irreducible instanton homology, something more classical. If you start with a knot in the 3-sphere, then plus or minus one half surgery on that knot can be thought of as surgery on a knot in RP3. You do 2 surgery on the unknot first. That embeds this thing as a knot in RP3. Do 0 or 1 surgery on that. If I look at the corresponding surgery sequence, which doesn't exist in the literature, but I claim kind of does exist, you get an exact triangle where the third group is whatever the instanton homology of RP3 should be, the irreducible instanton homology of RP3. This looks at irreducible, non-abelian representations of the fundamental group. Pi 1 RP3 is Z mod 2. It should be 0, whatever this thing is. So this cobordism map, the surgery triangle, should give me an injection on instanton homology I should be able to conclude. Same issue. On the other hand, if you write down, when you prove that this exact triangle exists, you have to prove exactness somehow. And if you run through the details of what that proof says, when one of these complexes is just 0 on the nose, what it does is the proof says the top map is an isomorphism. Here's a chain homotopy equivalence. Here's a formula for the inverse. More precise, what I can say is the inverse is given by a cobordism map. The inverse is given by counting instantons on this composite cobordism, the one that starts at 1/2 surgery, goes to RP3, and then goes to minus 1/2. And this composite cobordism has B plus equals 0. But if I just mean the actual usual induced map, that's 0 because it factors through the trivial group. Rather, what I mean is I'm counting instantons in a certain 1-parameter family of metrics. These kinds of things tend to appear in technical arguments in Floer theory, checking that 2 maps are chain homotopic. But here what I've got is a situation where I have a map which is chain homotopic for 2 different reasons. This gives me a reason for those. It relates the 2 reasons and defines a map. Yep?
Quick question, maybe this is a silly question. So why couldn't you do the same argument in +-1 surgery coefficients before in the original setting?
So it's just that there's not a nice, there's not a surgery triangle relating 1 surgery and -1 surgery to S3 itself. Yeah. You had to pass through that thing in the middle. Was a needle stick. Yeah. But we have another, we're going somewhere with this. The same kind of argument I wanted to do earlier does work now. The instanton homology of this thing is non-zero. I have a cobordism with B plus equals 0. It doesn't quite fit into the framework I laid out before, but some modifications of that lemma don't really change how it works. We get that 1/2 surgery and -1/2 surgery are different. And here I was stuck again, because this doesn't work for 1/3 or 1/4 and so on. What you get in general is some exact triangle relating -1 over n surgery to n-1 over n surgery to L of n1. And I don't care about n-1 over n surgery. So I get this, and it's cool, but I need a new idea. This is where Ali Daimi's work enters the picture. He, together with Lucas Kohler and Yi Shi, in 2020, introduced a surgery triangle which he won't let me call the CDX triangle. I have to call it the distance 2 triangle, but if anyone else wants to popularize the other name, please feel free. The key point, the reason we call this distance 2 is that normally there's a relationship between the Floer homology of P over Q surgery and R over S surgery when the corresponding matrix has determinant, let's say, ±1. Here, I want to relate 1 surgery and -1 surgery. Corresponding matrix has determinant ±2. I want to call this a distance 2 surgery. And they have an exact triangle relating the one homology, the instanton homology of one surgery, minus one surgery, and zero surgery. It's a little, well, I mean, to me it was a little funny. I think this shape is more familiar to people in Heegaard Floer homology. This looks like the surgery triangle for surgery slopes distance 2 apart. All the maps here are induced by cobordisms. When I mentioned this distance 2 thing, the natural cobordism you get has an L of n, is it L of n1? No. Has an L of PQ end, where P is determined by the determinant of this matrix. No. Of this matrix down here. So these cobordisms are cobordisms with some extra RP3 ends. It's not really significant in the way things develop. When you plug in the 3-sphere, I end up with almost exactly the same situation I was discussing before. I've got the bottom thing is 0, because Y is the 3-sphere. The cobordism map I like, or the cobordism map I'm looking at in the top row, is an isomorphism. B plus is wrong, but its inverse has the right B plus, and I win. You get that one surgery and minus one surgery disagree, because the L invariants disagree. But that doesn't get us 1 over n surgery. This kind of technique only works so far. Are there any questions about anything I've said so far before I move on? I think we'll get out of here early. Yeah. No, that's exactly it. Did I say something about the unknot? No, I probably should have. Oh, well. This is only true when K is not the unknot. Please, yep.
Is the general distance n surgery not known in instanton homology?
No. I mean, so one of these is what do we even mean by this? The C tilde stuff, the surgery triangle is not written down yet. It's lower on the priority list.
Was it expected that there'll be like one where that third term is like?
There's enough subtleties flying around that I'm not willing to make predictions quite yet. A lot of things match up, so I would be surprised if there wasn't something that translates that. But especially with irreducible instanton homology, which doesn't have a Heegaard Floer analog, I get more concerned. Also, I don't know what it is for rational homology spheres, what it means. So at this point, I want to say something about 1 over n surgery. And if you look at the exact triangles I've looked at so far, the conclusion I've used in both cases has been about a map that induces an isomorphism. The way I phrased the lemma earlier is if W induces an injection on instanton homology, I get an inequality. I phrase that because I want to apply this a couple times. I want to look at Floer's exact triangle, but also the distance 2 exact triangle applied to 2 different manifolds. If I look at this on the minus 1 over n side, I've got some triangle relating 0 surgery to minus 1 over n surgery to the next slope down the list. Down here I have a triangle relating 1 over n minus 1, and 1 over n minus 2. If you use these repeatedly, you can find out, you know what the ranks of these things are. They're just like, whatever this is, so that's k, the ranks of these things are nk. It's a linear function. And if you look back up at what I'm seeing up there, this has rank k, this has rank n minus 1k, this has rank nk. Those add up to n minus 1k and k add up to nk. And the only way that's possible to do in an exact triangle is if it splits. Similarly, in this second one, this looks like rank n, k, rank 2 times n minus 1 times k, rank n minus 2 times k, Add 2 of these up, you get the third one, and you find that these triangles split. One of these maps is an injection, and one of them is a surjection. From the first one, we get that the homology of -1 over n surgery, the invariant of -1 over n surgery is smaller than the invariant of -1 over n minus 1 surgery. Similarly, the second triangle gives us the same thing for 1 over n minus 1 and 1 over n. And I can chain these inequalities together until I finally am reduced to -1 and 1, which is what we were just doing over here, which was the case we finally handled a moment ago. So we've proven the cosmetic surgery conjecture for this sequence of slopes, the only one remaining being plus or minus 2. Sorry, I think I'm not used to the speed of slide talks. I tried to slow myself down, but I guess like I said earlier, no one will complain if we end a little bit early. I'm getting towards the end here, so I want to talk about some speculation about truly new structures involved here and how this relates to some of my other work with Chris Scaduto and Ali Daimi about these equivariant versions. It bothers me, among other things, that I can't do 2 surgery, that these techniques work for all 1 over n, but I have no idea how to do 2. There are a couple of things that seem natural to try, and they don't work. If I were to speculate about about the structure of this theory and what one might want to do next, part of the problem is that there's not a well-defined irreducible instanton Floer homology group in general for arbitrary rational homology spheres. You're fine for 2 surgery, but that's not the issue. But it does cause trouble when you're trying to compare these values, especially when you're trying to apply surgery sequences, like you said with, like Matt said, with rational homology spheres appearing. On the equivariant side, you do get something well-defined, and you see exactly what these terms depend on. These I stars come from the equivariant homotopy type of that complex C tilde, as opposed to a weaker notion of equivalence, opposed to equivalence in the derived category. And that homotopy type depends on a specific, some spectral data called the signature data function. There are a lot of these. There's like, take half of the size of your first homology group. You have z to the that many signature data functions. So if you're trying to get an invariant out of this, you're sad because you're not really sure how, there's not an invariant there. But one thing that's special is I mentioned these things are defined in terms of spectral invariants, Atiyah, Patoti, Singer, Eta invariants. The lens spaces are special. They have those computed for us already. And it turns out there is a unique choice of signature data function which gives P over Q surgery on any knot the same spectral information as P over Q surgery on the unknot. Barring technical difficulties, which don't matter in the remaining case we have, in the case that the Alexander polynomial is trivial, I can get a Chern-Simons filtration on these things, and I can define invariants of the P over Q surgery on a knot. And then, okay, you get some exact triangles associated with these. This is the right spectral data for all of that to work out. And you want to ask, how are these all related? Can I say something novel about 2 surgery or about slopes other than 1 over n? And what I can say today is in the following table. We know earlier in the talk we talked about the sequence of L invariants for 1 over n surgery. And we've got that great line going from the positive side to the negative side. Other surgery sequences involving lens spaces and other surgery slopes give me some of the other depicted inequalities here. And in particular, the invariant for 2 surgery is bigger than the invariant for 3 surgery, and so on and so forth. I feel like, intuitively, I want to say there should be some way to bridge the gap here, that this inequality is getting tighter and tighter and tighter. This is true in the one case that we computed something, which is not very many, so take that with a grain of salt. But even more than that, if these things are getting tighter and tighter and tighter, you might want to guess that there's some limiting object that you're approaching or maybe exceeding as you take n to infinity. So I want to stop there and say, what is that? If you have any ideas, let me know.